Okay, this week we will continue to fluid kinematics. Remember that before the midterm exam, we started fluid kinematics. In fluid kinematics, we learned the kinematics of fluid particles. It's not so much different from the kinematics of solids, but of course, the difference in the fluid particles can easily deform. This is the most important difference between the fluid particles and solid particles. Otherwise, they behave like moving solid particles. They translate, they rotate, but they also do some other deformations or motions. And in this chapter, we will see other kinematics properties of the fluid particles. In solid mechanics, remember that a solid rod, if you pull it apart, it will elongate. It's translation. It's the motion in linear direction. Or it can rotate like a shaft. It can have linear strain, and it can have shear strain. So these are the four different behaviors of solid particles. But when it comes to fluid particles, because fluid particles have also velocity, we do not deal with the translation, rotation, linear strain, or shear strain directly, but we deal with the time rate of change of them. So the time rate of change of translation, remember from physics, it's displacement per unit time, which we call it velocity. So velocity is rate of translation. It's the time rate of translation, which we call it velocity. We already saw the velocity in the previous chapter. We will review it anyway, but velocity is something that we already know. The second rate of motion is rate of rotation, which is angular velocity. If a fluid particle is rotating at a given, let's say RPM or cycles per second, then we can say that it has a angular velocity. Then instead of strain, linear strain, we deal with rate of linear strain. In solid mechanics, remember that we used delta over L, which is the strain. It means elongation per unit length. But in fluid mechanics, we use it as elongation per unit length per unit time. So it's the time rate of change of deformation per unit length. It's the strain, but per unit time. Similarly, shear strain is not taken as radians only, but radians per second, meaning that it's the shear strain per unit time again. So if you look at the picture on the right, you see that there are four kinds of motions. The first one is just a moving fluid particle. So the fluid particle is just moving from left to right. The second one is a rotating fluid particle. It's rotating counterclockwise. In the sea, you see a fluid particle being strained linearly. So it's just extending like a piece of plastic, let's say. And the other is undergoing a shear strain, which means it's been deforming in an angular way. So the shape of the square becomes like a trapezoid, which means its shape has changed because of the shear strain. So there are four kinds of motions that we will see in the fluid motion. First, let's remember the rate of translation vector, or just velocity vector. Velocity vector is given as the fluid three components of the velocity. The x component of the velocity is u, y component of the velocity is v, and z component of the velocity is k. Of course, they all may be a function of x, y, z, and also t. So each of them can be a function of space and time. The second kinematic motion is the rate of rotation, or just angular velocity. We assume that this fluid particle, it was a rectangle like this in the beginning, but it has rotated in counterclockwise and it has taken this shape. But the bottom part has rotated by alpha A, and the top part has rotated by, or the left part has rotated by alpha B. So the average rotation is alpha A plus alpha B divided by 2. So this is the rotation of the fluid particle. If you take it by per unit time, then the time rate of change of this average angular displacement is d over dt. Average rotation. And if you take the drawings and if you work on them, then you will see that the time rate of change of this fluid particle is 1 over 2 dv over dx, which is the change of the v velocity in x direction minus du over dy, which is the rate of change, the variation of u velocity in y direction. So the rotational velocity or angular velocity of a fluid particle is given as 1 over 2 dv over dx, the partial derivative of v velocity with respect to x, minus du over dy. Of course, this is in only 2 dimensions, so it's only in xy dimensions, xy plane. So the fluid particle can have other rotations. It can rotate about any axis. So if you consider all the axes, this one is the rotation on xy plane. This one is the rotation on xz plane. And this one is the rotation on yz plane. So it's a vector. It has 3 components. It has I component, j component, and k component. And this was only the k component because it rotates. If you consider this table to be xy plane, the rotation is like this. And this k vector gives you the rotation size. So counterclockwise rotation of this vector, of this fluid particle, will give you a positive direction of k. And it's only xy plane. So if you consider the other planes will also have the components of the angular velocity. The third motion is the linear strain rate, which is actually the strain rate, strain per unit time. And let me remind you the strain. The strain is given as delta over L, which is the elongation in meters per meter length, per meter of the material. So it looks like it doesn't have a unit, but its unit is actually meters per minute. But if you consider it per unit time, then you get the linear strain rate in x direction to be du over dx, because it has the units of 1 over second. This cancels that. And the linear strain rate in y direction is this. Similarly, linear strain rate in z direction is that. They just mean that the fluid particle is elongating as du over dx per unit time. This is the theoretical explanation of this, so you can just skip this. It's not so important. The volumetric strain rate, sorry. There is also the volumetric strain rate. Volumetric strain rate is the change of volume per unit time. Normally, we take the change of volume as dV over V, which is the change of volume per unit volume. This is normally under static conditions. But because fluid particles are moving, we have to take time rate of change. So we take it as per unit time of change of this unit change of volume. So it's given as 1 over V, dV over dt. It can be written as the summation of Exx, Eyy, Ezz. And if you put everything in terms of the derivatives, du dx, dv dy, dw dz, you get the volumetric flow rate to be du dx plus dv dy plus dw dz. What happens if the fluid is incompressible? What is an incompressible fluid?
An incompressible fluid, wouldn't it basically be a solid?
Not necessarily. Fluid, liquid is also incompressible because however much pressure you apply on it, you cannot change its volume. So its volume is constant. What happens when something is constant when you take the derivative? Zero. So if it's an incompressible substance, then this is going to be zero for incompressible substances. So it means that the summation of the E epsilon xx, epsilon yy, and epsilon zz is zero if it's an incompressible substance. Otherwise, it doesn't have to be an incompressible substance. For instance, air is being compressed in the cylinder, as you can see. Because air is compressible, as it's being compressed, its pressure is increasing, meaning that its volume is decreasing, so that its density is increasing. It's being compressed. And as a result of compression, an air parcel is just an enlarged particle. It can be a very small particle, becomes volumetrically smaller. So it's just a volumetric strain in negative direction. It's losing some of its volume. So this dV will be actually smaller than zero in this case. On the other hand, if this was liquid, so you apply pressure on the liquid, you can change the volume only by a very small amount. Theoretically, we call it incompressible, but normally it can be compressed by only a little amount. And this is why we can use hydraulics. In hydraulic systems, the hydraulic cylinder and hydraulic piston pushes this liquid, the hydraulic, because it doesn't get compressed, it has to transfer the force to the other side. This is how the hydraulic systems are working. The shear strain rate, the fourth type of motion in fluid particles, is the shear strain per unit time. So the shear strain per unit time is calculated from not only as the angular change, because in solid mechanics, when we calculate the shear strain, it was just this angle. But now we have to deal with the time rate of change of it. So the time rate of change of it is the difference between alpha A minus alpha 2 divided by 2. So the time rate of change of this property will have 1 over 2 du dx dy plus dv dx. If you compare this shear strain rate with the angular rotation, you see that the only difference is this sign. So they are very similar to each other, but the only difference in the angular velocity, the sign in between is minus, whereas the angular in the shear strain rate, it's plus. So this is the only difference between the angular velocity. And this is only xy, so you will have also zx, which is the shear strain on zx plane, and yz, which is the shear strain on yz plane. So up to now we have three linear strains, which are epsilon, three linear strains, which are epsilon xx, epsilon yy, epsilon zz. These are the linear strains. And also we have 2 times 3 shear strain rates. Why? We have epsilon xy, but we also have epsilon yx. Then we have epsilon zx, but we also have epsilon zx, and epsilon yz and epsilon zy. So it means that we have a total of 9 strain rates. 3 of them are linear strain rates and 6 of them are shear strain rates. If you put them in a tensor, you don't know what a tensor is. A tensor is something like a matrix. It's not a matrix, but it looks like a matrix. Never mind the name. But on a tensor, you can show all these 9 components of the strain rates. And on the diagonal, you see that there are the linear ones and the non-diagonal ones are the shear strain ones. So this is xy, epsilon xy. This is epsilon xz. This one is yx. And this one is yz. And this one is zx. And this one is zy. So if you compare them, you will see that actually xy and yx is the same. Du dy plus dv dx. And this one is dv dx plus dv du dy, which are the same. So it's like the stress, shear stresses. Remember from the shear stresses, tau xy is equal to tau yx. So similarly, epsilon xy is equal to epsilon yx. So the shear stresses on a plane are the same as tau xy being equal to tau yx, and similarly, shear strain rates are also equal on a plane as epsilon xy being equal to epsilon yx. So these are a lot of theory, I know, but they are very useful in explaining the fluid motion. So as you can see, a fluid particle, as it moves along a path, can have 4 kinds of motion. It can first translate like this. It can rotate about it. It can have strain, like it can elongate or it can contract, and also it can have shear strain. So not only the linear shapes, linear dimensions can change, but also the angles can change. So we have 4 kinds of motions of a fluid particle as it moves along the path. Also, it can be also a volumetric strain in 3 dimensions. But volumetric strain is just a result of the linear strain. So the summation of 3 linear strains are just volumetric strain. So it's not actually something different. Now we have a numerical example about all these things. Remember this flow in the previous chapter. In the previous chapter, we have studied the flow that takes place from the top to the bottom left. So we actually analyzed only this part, and it was like the flow in an entrance of a water dam. If you go to the previous chapter, you will understand what I say. So we have studied only this part. And in this part, the translation rate of translation vector, which is the velocity vector, was given as the u component to be this. This was the u component, and v component to be that. So we would like to find out whether this flow is rotational or not. Rotational means the fluid particles are rotating or they're just moving without rotating. They are sure translating because they have velocity. We know it from the u and v velocities. So as it moves along the path, we know that it has a u velocity and v velocity. So these are the streamlines, and velocity vectors are always tangent to the streamlines. So streamline is a line to which the velocity vector is tangent at all the points. This is the description of a streamline. And because it's two-dimensional, there is no w velocity. By definition, it's two-dimensional. It's xy plane. The w velocity is explained as is given as 1/2 dv dx minus du dy. What is dv dx? It's the x derivative of v velocity. V velocity here, there is no x in it, so it's 0. And the second term, du dy, it's the y velocity of y derivative of u velocity. There is no y here, so it's 0. Then we get 0. It means that this is a irrotational, it's called irrotational flow, meaning that the fluid particles are not rotating as they move in the path. What do they do instead? As you can see, the fluid particle is moving from this location, for instance, to that location. There is no rotation. As you can see, it has moved like this without being rotating. But if you check the strain rates, then you will see that epsilon xx, which is defined as du dx, it's 0.8 second to the minus 1, and epsilon yy is minus 0.8 second to the minus 1. It means that it's elongating in x direction and contracting in y direction. Because it's incompressible, it was given the sum of the epsilons must be 0. So epsilon xx plus epsilon yy plus epsilon zz must be 0. And you see that the summation is 0, meaning that it's incompressible. So volumetric strain rate is 0, even though it's changing shape from here to there like this, or from here to there like that. The volume does not change. Even if it's changing the shape in x and y direction, the volume does not change. And we see it here, the sum of the linear strain rates are 0, meaning that the volumetric strain rate is 0, or it's incompressible. Then we would like to find out whether the shear strain has a non-zero value. We check the shear strain rate. The shear strain rate is found from this expression. And we find that the shear strain rate is 0. As you can see, it keeps its shape. It was a rectangle, but still a rectangle. So the angles do not change, meaning that there is no shear strain. And finally, it was shown that it's incompressible because the summation of the linear strain rates are 0. So this was a good example to understand what all these mathematics are all about. The math seems to be a little bit complicated, but when you apply it in a real life example, then it's very much explaining. Because the fluid particles can rotate, then we define something as vorticity. Actually, you may have heard of vortex. I don't know if you have heard of vortex. Vortex is a rotating motion. The plural of it is vortices. Let me show you something about the vortex and vortices. So, it's very interesting, right? It's a landing aircraft, and as it lands, because of the fluid moving at the tip of the wing, has a rotating motion because underneath the plane wing there is low pressure, high pressure. On the top of the wing there is high pressure, so air moves like this, and this motion can be seen as a vortex. So after this, I can move explaining what a vortex looks like. So the behavior of the rotation is explained by the term of vorticity. Vorticity is a value that tells you how much rotation is included in the fluid motion. It's actually mathematically double the rotation vector. So it's nothing but vorticity vector is given with zeta. Zeta is nothing but 2 times omega. Omega is the rotation vector. Mathematically, it's just 2 times the omega vector, the rotational speed vector, angular velocity vector. I skipped this. I don't know if you have seen the nabla operators, the cross products. Did you see them? Okay. So we have this operator. For instance, this one will produce something. However, this one will produce a totally different something else. This is called curl, and this is called divergence. Divergence of the one vector is actually this. So if you take the divergence of velocity vector, you will get this. On the other hand, if you get the curl of the v vector, you're going to get the vorticity vector. Let me skip all these details of math. If in a flow field, the flow particles are not rotating, they're just moving on a straight path. We call this field, flow field, as irrotational. On the other hand, if the fluid particles are moving as they move in a straight line or in a line of the flow path, then this region is called rotational. I will come back to this explanation of the flow over a flat plane. Let's suppose that we have a flat plane like this, like the table, and assume that wind is blowing on the table. Because the fluid particles will stick on the table, they cannot have any velocity. So the fluid particles, the molecules, will have zero velocity on the table. But as we move away from the table, the molecules or the particles will start having some velocity. The farther you're apart from the table or plate, the more the velocity. Because what affects this change in velocity is what we call viscosity. Viscosity is the internal friction in the fluid. So because of the viscosity, we have zero velocity here. Just above of the plate, we have some velocity. Just a little bit above, we have more velocity. So it means that when you go away from the plate, your velocity starts from zero on the plate and increases to some point, which we call boundary layer. We will see it later. And above the boundary layer, the fluid particles do not have any information that there is a plate there. So the information, because of the viscosity, can be transferred only in boundary layer thickness. It can be just a few millimeters, but in atmospheric phenomena, it can be 100 meters. Around the ship, it can be 20 centimeters, whatever. When you go by your car, you can see light objects like flies or leaves moving along a line on the car. They follow a path around the car, right? So they just move about the car. And it's actually just inside the boundary layer. So under the friction effects, under the viscosity effects, they move along a line which surrounds the car. It's a streamline. So after explaining what is the flow around on a flat plate, we have the flow on a flat plate, and you can see that this is the boundary layer I have just explained. In the boundary layer, we have a change of the velocity from zero to free stream velocity. It's called a free stream velocity. And above the free stream, above this layer, the velocity is the same. So it's only the boundary layer, it's the region that we call boundary layer, in which the velocity changes from zero to something, to some uniform value, and from this point on, it doesn't change anymore. So look at one of the smileys. The smiley has a higher value, higher velocity at the top than at the bottom. What would happen to the smiley? It will rotate, right? It will rotate like this. This is why we call this region as rotational region, because fluid particles rotate in the boundary layer region, which is the region where the viscosity effects are felt. Outside the boundary layer, the viscosity effects are not felt because the fluid moves as a whole without having any velocity changes between the layers. So outside the boundary layer, which we call irrotational region, the fluid particles do not rotate. Sometimes, depending on the geometry, instead of Cartesian coordinates, we may have to use the cylindrical coordinates because it's easier, especially if the flow is circular, then using the cylindrical coordinates are much easier than the Cartesian coordinates. In the case of cylindrical coordinates, we will be using some other mathematical nomenclature, but in 2 dimensions, we have just the vorticity of this. So this is the vorticity on xy plane only, and it has a vector of k because of the sign of the vector. This is a counterclockwise rotation, so counterclockwise is positive. Counterclockwise moment, counterclockwise angle, counterclockwise rotation, they are all positive because they all just give you positive k vector, right? So as you can see, the fluid particles are rotating in counterclockwise direction as they move along the path. So they are moving along this path, and meanwhile they are rotating. And the rotation, if it's only on xy plane, is given as this vorticity. Otherwise, if it's having all kinds of motion around 3 kinds of axes, then you will have a vorticity vector given like this. This is a solution from a CFD package. Have you heard about CFD? Did you hear about CFD? Computational fluid dynamics. Computational fluid dynamics is a very powerful tool when it comes to heat transfer and fluid dynamics problems, because as you can see, there is a lot of math included in the fluid dynamics, and it's only 2-dimensional. And when it's 3-dimensional, it's very complicated to solve by hand. But numerical methods like CFD, the computational fluid dynamics, can make it very easy to have solutions of the flow problems. There are packages like Fluent by ANSYS or by some other companies, and you just create the geometry first. So this is your geometry. It's a flow around the block. So it's a block like this, and we are analyzing the flow around this block, right? So we have the geometry first, then we define the velocities, maybe the pressures, then we run the program. And after running the program produces the velocity vectors, the pressure distributions, the vorticity distribution, and this is called a counter plot. Maybe you remember it from 2 weeks ago. In counter plots, you have a colorful plot where every color represents a some value. For instance, here, sorry. Alo. Ha, buyurun Banu Hanım. Tamam, ben dersteyim, dersten çıkınca alırım. Teşekkür ederim. Tamam, evet, sağ olun. Pardon. So, in a counter plot like this, you have to be given a scale of colors here, right? You need to be given a scale of colors here, showing red has this value, orange has that value, and as it goes below, the smallest value might be negative, can have blue. In any case, by looking at this, we see a lot of difference in vorticity, meaning that the intensity of the rotation in different places. At the edge, we have a high vorticity. Why do you think it happens like that? Because as the air shoots the edge, then the derivatives of the velocity will change suddenly. du dy, du dy, and dv dx will change suddenly, right? And this sudden change, by the definition of the vorticity, will create a high vorticity. Mathematically, it will create a high vorticity. Physically, you can have this high vorticity, which will cause a rotation. So that's why on this corner, you're going to have a rotation of air like this. And this blue color gives you a rotation in clockwise direction, which means it's negative. That's why in this scale you have the blue color at the bottom. On the other hand, at the back of the block, because the air separates due to the pressure drop, I will explain it later, at the back, then we have a backflow. It occurs in the hatchback cars. That's why you have a glass cleaner at the back of the hatchback cars. You don't have it on sedan cars, but on hatchback cars, you have a windshield cleaner at the back, right? Because it has a flat back like this, and because of this flat back, there is a vortex or vorticity at the back of the car, which will create a vacuum, and this vacuum will suck the dust and will make this window or glass dirty. That's why you need a cleaner there, and you don't need that in a sedan car. So in the front, you have a clockwise vortex, which means it's negative. It's like this, clockwise. On the other hand, at the back, you have a counterclockwise vortex, which means it's positive. So this is just the interpretation of a solution of a CFD problem about the flow around a block. Only the half of the block is taken because it's a symmetrical problem. So in order to save computer resources, if there is flow around this one, you can just take a symmetry line because you know the top and the bottom are the same. So you can only work with the top side because the bottom is the symmetry. And this will save a lot of computer time, a lot of computer resources like memory and everything. So the same thing happens actually at the symmetry. There is a numerical question regarding the vorticity, but we don't have that time. So let's have a break of 10 minutes. If you don't have any questions, do you have any questions? How do you find the level of math in this chapter? It's not so easy, but not so difficult either.
Just the math itself.
Just the math itself.
If you are trying to calculate, if you are trying to compute on these functions, well, they will just be putting in the numericals. But
yep.
If you were to ask me to just drive any of these stuff, it would be incredible.
No. Of course not. And how about the physical interpretation of the problems? Do they make sense?
Yes, they do.
Okay. So let's have a break of 10 minutes. Then we'll be back at 3. So, no, 2. In this example, we are given a 2-dimensional flow for which we would like to find whether the flow is rotational, and if it is rotational, we are going to find the vorticity of it. So the flow is given as, the flow field, velocity field is given as x squared I, which means u is x squared, and minus 2xy minus 1j, meaning that v is, let's put the minus in the front, 2xy plus 1. So these are the velocity component of the velocity field. In 2 dimensions, the definition of the vorticity is dv dx minus du dy k, because it's on xy plane. So we find that the vorticity has a non-zero value, and it's not constant. It changes with y. So for larger values of y, it has a larger vorticity. For the value of y equals 0, it means it has a 0 vorticity. It has a minus sign in the front of it. What does it mean?
It means it's
Clockwise.
Clockwise.
So the fluid particles rotating clockwise as they move along the path. So let's take a look at the streamlines if they do it correct in the clockwise direction. So by the way, if zeta is minus 2yk, then omega is just yk.
Sorry.
So these are the streamlines. It looks like the streamlines in the previous problem, but they are completely different. So the streamlines have been obtained. It's not the part of the solution of to obtain the streamlines, but suppose that the streamlines are already given. So what is a streamline? Streamline is a line to which the velocity vectors are tangent at every point. It means that velocity vectors are always tangent to it at each location. So at any location, the velocity vectors are tangent. In the beginning, at t equals 0, the fluid particle is a rectangle. Here, in 0.25 seconds, it has come down to this location from here to there. But meanwhile, it has changed shape, right? Not only it has elongated, but its shape has changed in angular direction also. At t equals 0.5 seconds, it has elongated more, and meanwhile it has contracted like this, because what is the condition for the compressibility? For the compressibility, it's necessary to have 1 over v dv dt to be 0. So it means that the sum of the linear strain rates must be 0. So if you take the du dx is 2x, dv dy is minus 2x. If you sum them, you will get 0. So it means that it's incompressible. And the definition of vorticity is given as dv dx minus du dy k. So can you see that the fluid particle is rotating clockwise? So it was here, it has rotated like this, it has rotated more. So it's rotating in clockwise direction as it moves along the path, right? How about the strain rates we have already found? The exx is, epsilon xx is 2x, epsilon yy is minus 2x. How about the shear strain rates? Can you say anything about the shear strain rates? Then you need to check the shear strain formula, right? The shear strain formula had a positive sign here. So if you check them, that you will see that the shear strain is also non-zero. So it's also distorting in an angular way, not only in linear way, but also angular way. This is what I said to you already, that sometimes we may need to use cylindrical coordinates depending on the velocity vector. If velocity vector is given in Cartesian coordinates, then you can use the formulas in Cartesian coordinates. But if you are given the velocity vector in cylindrical coordinates like u theta, theta is the angular velocity, or ur is the radial velocity. In this case, you will have to use, or uz, you will have to use the cylindrical coordinates. In 2 dimensions, it looks very complicated, but in 2 dimensions, the vorticity vector in cylindrical coordinates is 1 over r, d, r times u theta. U theta is the angular velocity. Ur is the radial velocity. So dru theta divided by dr minus dur divided by d theta. It means this is the derivative with respect to r, and this is the derivative with respect to theta. Here also you can see that the fluid particles are rotating as they move along the path. And what is the rotation sign? What can you say about the vorticity? They are rotating clockwise, so it means that my thumb is showing minus k, so clockwise is minus always. We have some examples of cylindrical coordinates. We have 2 different flows. There will be another one. The first flow is solid body rotation. Solid body rotation means that about an axis, like a whirlpool. You know what whirlpool is, right? Mm-hmm. Whirlpool. Like a whirlpool, the fluid is rotating, like a tornado, for instance. So fluid particles are rotating about an axis, like a whirlpool or like a tornado. If it's a solid body rotation, the fluid particles, the smileys, will rotate as they move along the paths, right? On the other hand, if it's a line vortex, then as you can see, the fluid particles, the smileys, are not rotating as they move along the path, but they just stand still. In the solid body rotation, there is no radial velocity. You can see that there is no radial velocity here. All the velocity is tangential velocity. So the only velocity is tangential velocity. And this tangential velocity is given as omega r, meaning that the tangential velocity is 0 at the center, and its value is increasing as we move on the radius, right? So it's like a rotating rotation about an axis. So right on the axis, the velocity is 0, but away from the axis, the rotation velocity will be increasing. I mean, even if the tangential velocity is the same, the angular velocity is the same, the tangential velocity will increase if you move away from the center. So this is what happens. You have a constant radial angular velocity, and its value is increasing. The tangential velocity is increasing with the radius. In the case of line vortex, it's given as k over r. It means that right in the center, the tangential velocity is infinite. This is what happens inside in the core of a tornado. Mathematically infinite, but physically not infinite. But it means it's very large. And away from the radius, its value becomes less and less. So let's see what happens in both cases. In the first one, we have a vorticity of 1 over r, this formula, dru theta versus dr minus dur. with respect to d theta, we just put the u theta value here. This is the u theta value. I need to make a phone call because someone is calling me. So, for the solid body rotation, the tangential velocity is given as omega r, and for the line vortex, the tangential velocity is given as k over r. In the line vortex, of course, sufficiently away from the radius center, the tangential velocity will be 0 because it gets smaller and smaller as we move away from the center. So we will use the definition of the vorticity. R times u theta, we will take the derivative of this with respect to r. So omega r times r is omega r squared. The derivative of this with respect to r is 2 omega r divided by r, which will give you 2 omega. So it says that the vorticity is 2 omega. If vorticity is 2 omega, what is omega? Vorticity divided by 2, which is omega, which we should expect, right? So vorticity is 2 times omega, and it's actually twice as much as the angular velocity. If you do the same thing in line vortex, 1 over r, in this case, we need to multiply the u theta by r. So when it's multiplied by u theta, we just get k. So the derivative of a constant is 0. So in a line vortex, we have 0 vorticity. How can we see this? We see that in the solid body rotation, the smileys are rotating at a velocity of omega, but in the line vortex, the smileys are not rotating. They just stand still. As an example of solid body rotation and line vortex, for instance, this roundabout, the children on this roundabout will rotate with the roundabout, right? So if you consider this as a smiley, this smiley will look like that, like here. So this is like the first example, the solid body rotation. However, in Ferris wheel, as the Ferris wheel rotate, you know the seats do not rotate, right? Rotates just stay as they are. So it's not rotational. Here we have vorticity greater than 0, but here we have no vorticity. So this one can be considered to be rotational. This is just the analogy. They're not fluid flow, of course. Just as an analogy, this is like a rotational flow, whereas this one is a non-rotational flow or irrotational flow. Now, a similar thing to be used with the cylindrical coordinates. In this case, we are given a line sink. What's a line sink? Consider a hole and flow is coming into the hole. but without any rotation. Sometimes it happens. So all the flow is coming into a hole without having any rotation. In this case, we can see that there is no tangential velocity, but there is only radial velocity, right? Because all the flow is coming into the hole. It's called a sink. And it's here, the u theta is 0, no tangential velocity, but there is radial velocity, and this radial velocity is given as v dot, which is the volumetric flow rate, divided by 2 pi L, it's given, divided by 1 R. It means that very far away from the sink, the tangential velocity is 0, 1 over R. Very close to sink, it becomes very large, and mathematically it becomes infinite right in the center, right? But it's not physical, of course. Now we will check if there is any vorticity here. For sure, there shouldn't be any vorticity. Nothing is rotating. But mathematically, we need to show it. We will use the same vorticity formula in 2 dimensions of xy plane. So we will be using this. R times u theta is R cancels, so we have a constant value. So the derivative of a constant is 0. Then we have d theta u r, d theta. Then we have d theta u r, d theta of this whole thing. There is no theta in it. It's also 0. So you can see that the vorticity is 0, as we expect. It's irrotational also. Any questions so far? Good. Now we will start a different section, Reynolds transport theorem. Reynolds transport theorem is very useful in conservation theories. We have conservation of mass, conservation of energy, and also conservation of momentum. So in fluid flow, we have to make sure that mass is conserved, energy is conserved in thermodynamics too. Mass is also conserved in thermodynamics. And from mechanics, momentum, which is m times v, this is called momentum, is also conserved. In order to have the conservation equations, we use a generic formula, Reynolds transport theorem, and Reynolds transport theorem can be connected to all kinds of conservation equations, including mass, energy, and momentum. So let's remember from thermodynamics that we had 2 different systems. One is closed system, the other is open system. What was the difference between them? Do you remember? In a closed system, no mass was crossing the boundaries, right? In an open system, mass can cross the boundaries. It can come in, it can go out. So this is the difference between the control mass or closed system and control volume or open system. So the first bottle of spray is a control mass or system. It's just called a system because, as you can see, it includes the spray itself, so that no mass is actually crossing the boundary, because you have also included the spray itself. On the other hand, if you choose the boundaries to be only the control volume, then mass is crossing the boundary of the control volume. So this one is a system, this one is a control volume, and Reynolds transport theorem gives us the relationship between the system and the control volume. So system, Reynolds transport theorem, control volume. It's a link between the system and control volume. Here we have, there's a flow in this diffuser. Remember that in the nozzle, there's an acceleration because the cross section is getting smaller, meaning that the flow must accelerate to have the same flow rate. In a diffuser, we have a deceleration. Flow will slow down because the mass flow rate will be the same. Anyway, in this diffuser, we have chosen a control volume. This is the control volume that we have chosen. And the flow takes place from the left. So at the time zero, we have the control volume and the system overlapping on each other. But at a time of delta t, the system will have moved like this. So what happens is there will be a reduction here, whereas there will be an increasing there. So this is what happens inside the control volume, the change in the control volume, the reduction amount from the control volume, and added amount to control volume. Mathematically, we can just show this as at delta t seconds later, we have the system at delta t seconds later can be written as the control volume at delta t seconds later, the left amount plus the entered amount. So this is the entered amount, this is the left amount. So we can show it mathematically as, for the whole system, the change in the control volume, the left amount plus the entering amount. If you use the time rate of change of this, you are going to get the time rate of change of B. B is an extensive property. Remember what the extensive properties is? Extensive property can be mass, can be energy, can be momentum. And what was the intensive property? Intensive property is independent of the mass, right? For instance, temperature is intensive. If I divide this room by 2, the temperature won't change, or the pressure won't change, but the mass will change. So mass is extensive, whereas temperature or pressure is intensive. How about the density? Is density extensive or intensive? Intensive, right? If you divide this room to 1,000 pieces, if it's homogeneous, the density will be same in all the place. So if you divide an extensive property by mass, you get the small case b, which is an extensive property. So this is intensive property. So this one, the capital B is an extensive property, and small case b is an intensive property. If you want to change, if you want to find out the changes with time, then you can take the derivative of each term here with respect to time. The first term is going to give you dB system with respect to dt. So this B can be any property, any extensive property like mass, energy, or momentum. So here it means that the change of this property with respect to time, the first term. Then we have the change within the control volume. Then whatever comes into the control volume, then whatever leaves the control volume. I will explain this to you with a good example, but take it as it is for the time being. But mathematically, it says that the property B is being conserved. In total, the change in control volume minus the left amount plus the entered amount will be something constant. Meanwhile, you can also, because the small case b is the intensive property, which is the extensive property divided by mass, and remember that mass flow rate is rho times A times V, then you can write the terms here, the B dot term here as B1 rho VA, this is M dot, and B2 rho VA, this is M dot again. So mathematically, the leaving and entering amounts can be written by small case b, the intensive property, times m dot for the out as well. If you have infinite numbers of inlets and outlets, so instead of taking the summation of rho VAs, the summation of rho B VAs can be given as an integral, and in the integral you will take the integral for the whole area. This is the whole area. Integration is performed on the whole area. You have rho already, B already. What do you get when you have V scalar product N? What is the mathematical meaning of it? What is N, by the way? N is the normal unit vector, right? When you find the scalar product of V and N, what do you get? Yeah, you find the component of V in the direction of normal, right? Because mathematically it will be V cosine theta. So V dot N is actually V cosine theta, which is actually the normal component of the velocity. Why do you need the normal component? Because you are always interested in the component which is normal to the surface. It has to leave the surface in a normal way, right? In a perpendicular direction. So this is why you can show it as V dot N scalar product, which will give you V cosine theta, which is the normal component of the velocity. So actually you have written everything to represent this, because here V and A are normal to each other. But on this boundary, to make it sure that the velocity component is normal to the surface, then you need to use it as V dot N. And the integration around this surface will give you the net inflow of the, or outflow of the extensive property of M. So if extensive property of B, if B is mass, then this integral will give you the net mass coming in and going out of the control surface. How about the first part here? The first part can also be written as, the B can be written as rho times B times dV, because remember that small case b is B over M, and M is just rho times V. So you can combine everything inside this integral, and this integral will be performed over the volume. The first integral is performed over the area, so this is a two-dimensional integral, but this one is a three-dimensional integral because it's performed over the volume. So if we put everything inside the theorem, we have the change within the system, which is equal to change within the control volume, then net incoming and exiting amount. So we have written the same thing here in a more mathematical way using the integrals. So the same thing can be written as integrals. The time rate of change of extensive property B for a system is equal to time rate of change of this extensive property inside the control volume plus the net amount of this property coming to control volume and leaving the control volume. Some will be plus, the entering ones, the leaving ones will be minus. Sometimes it's also possible to move this derivative to inside the integral. So when you do it, it looks a little bit different, but it's just another form or another alternative form of the Reynolds transport theorem. So by using the Reynolds transport theorem, we can always write all three conservation equations, the conservation of mass, conservation of energy, and conservation of momentum. Sometimes there may be cases that the control volume may be moving, like this car. In this case, you just need to replace the velocity here with the relative velocity. If it's moving, we're just going to move this velocity with relative velocity, and all the rest is the same. So instead of using the velocity directly, we're just going to use the relative velocity, and all the other parts of the theorem is the same. If it's a steady flow, meaning that inside the control volume does not change with time, it means that the time derivatives will be zero. So in steady flow, this whole thing will be zero. So in the case of steady flow, we have only the term that has the amount of B entering and leaving the control surface. Again, it's also possible to write the net amount of this. By the way, this is also called flux. If the flux, the B intensive property is constant, if B is constant, then we can write the amount of flux coming into the system or leaving the system as B average times m dot r. M dot r is the relative one. If there is no motion, then you don't need to use m dot r, just use m dot. So in this case, you have the change in the system, change inside the control volume with time, the net amount of the property leaving the control volume, and net amount of the property entering the control volume. If you have, for instance, one inlet and two exits, then this will be the inlet part. You have only one, but at the exit you have two exits, so you need to take the summations of it. You can also write the m dot as rho VA, of course. When you do it, you have the expansion of m dot as rho VA. There may be different representations of this Reynolds transport theorem, but whether they look more mathematical or more practical, they they represent the same Reynolds transport theorem. We have already seen this, the general Reynolds transport theorem. The derivative is taken to inside, and nothing else is different. In the beginning, we have learned the Lagrangian description of the fluid flow. In the Lagrangian description of the fluid flow, we consider each particle, and by using the derivatives, we get Eulerian description. In Eulerian description, we consider the flow itself, not the particles. And the connection between the Lagrangian description and the Eulerian description is called the total derivative, or material derivative. In the Reynolds transport theorem, the system and control volume is connected to each other with Reynolds transport theorem. And at the end, actually, they will be representing the same conservation equations, whether you use Lagrangian descriptions, which use derivatives, or T, or Reynolds transport theorems, which use integrals. So Lagrangian, the material derivatives use the differential approach. However, Reynolds transport theorem use integral approach. So after having so much theory about the Reynolds transport theorem, let's see what exactly they are used for. First of all, we have the simplest conservation mass, which means that the amount of mass must be conserved. Let's consider this system. In the system, there is no mass crossing the boundary, which means the total mass is what? Constant. When total mass is constant, what happens to the left-hand side term? What happens to this? It becomes zero. So when it becomes zero, the Reynolds transport theorem is the left-hand side is zero. Then you have dm cv dt, which is the change of the mass within the control volume, plus m out minus m in. Because dm dt is zero for the system, because the mass of the system is constant. Can you give an example of this? The net of the incoming mass and outgoing mass is giving the change inside the control volume. Can you give an example to this? There's a bathtub, right? And there's a hole at the bottom of the bathtub. Water comes in as a flow rate as in m in, and water leaves the bathtub as m out. So what happens if m dot in is greater than m dot out? What happens to
The tub will start to flow.
dm divided by dt, the mass of the water inside the bathtub, which is the control volume? It will increase, right? Otherwise, it will decrease. So what this says is, if the amount of incoming mass is greater than the outgoing mass, the mass of the control volume will increase, otherwise it will decrease. What does it mean to have this one to be zero? Yeah, incoming mass flow rates are equal. So the application also conservation of mass is quite straightforward, and it's quite clear to understand the meaning of the conservation of mass. It's also called continuity equation. Sometimes it's called conservation of mass, sometimes continuity equation. Linear momentum equation. You have taken physics. In physics, the momentum, which is a vector, is given as m times v, right? According to Newton's first law, statics, the first part of the mechanics, according to Newton's first law, if an object is stationary or if it's moving at a constant speed, what is the summation of the forces acting on it?
It's zero.
Zero. So in statics, sum of the forces is zero if it's stationary or if it's moving at a constant speed. On the other hand, if the body is accelerating under the effect of the applied forces, what would happen?
It should be greater than zero.
Sum of the forces will be equal to m times a. And this m times a is actually the time rate of change of momentum, right?
It is.
Because m moves out, dv dt is a. So if the time rate of change of momentum is non-zero, then the sum of the external forces are non-zero, meaning that the body will be accelerating. This is called the linear momentum equation. If sum of the forces are zero, then the momentum is conserved, meaning that the value of the momentum is constant because the derivative of a constant is zero. So in the case the momentum is constant, whether it's stationary or moving at a constant speed, then the momentum is being conserved, the conservation of momentum principle. If on the other hand, if it's accelerating, it means that the applied forces are non-zero, so it has to accelerate. This is why, don't do it, but if you jump from this window, you will accelerate. Why? Because the gravitational force will be acting on you, and this acting of the gravitational force will cause you to accelerate at an acceleration of g. G is 9.81 meters per second square. The third conservation of equation, the first one was conservation of mass, the second one was momentum equation, and the third one is conservation of energy. Energy does not, cannot be destroyed, nor can it be created. So it can only change, right?
Yes.
In thermodynamics, meaning the energy can be either work or heat. In thermodynamics, we have seen them both, but in fluid mechanics, we will mostly use the work part because we will not be dealing with heat. So if the system dE dt system is zero, then similar to the conservation of mass, we have this. The incoming total energy minus exiting total energy will be causing a change within the system. It's actually the first law of thermodynamics, because in thermodynamics, remember that you have written net Q minus net W is the change of energy within the system. So per unit time, you can do it like this. And if it's a steady state situation, this will be zero, otherwise it will be transient. In any case, it looks like very much the conservation of mass. And for the energy transfer in and out of the system will be taken as only the work transfer to the system, not heat transfer, because this was already done in thermodynamics. Any questions? Okay, let's have another 12 minutes, then we'll be here at 3 o'clock. The conservation of mass is very easy to understand, so I just skip it. We will continue with the momentum equation, then we will go on with mechanical energy equation. In momentum equation, we need the forces to be acting on fluid particle or on a surface, and in return of this, there can be either a motion, or if it's a static condition, the fluid will be in stationary situation. Normally, if there is a motion in a fluid, then the forces may be either normal forces or tangential forces. Normal forces are actually the pressure forces, and tangential forces are shear forces. So as a resultant of them, the fluid can apply a force, a total force, on a surface. As a matter of fact, if there is a tangential force, then the fluid must move. So no motion, no shear. The water inside the glass do not have any shear force, but when you start to pour it, the shear will develop. So shear means there has to be some motion inside the fluid. Let's see the situation in a example where there are two pipes with different diameters connected to each other. So this is the pipe 1, this is the pipe 2. Flow comes in and goes out. At the inlet of the pipe, we have the normal force, the pressure force. At the exit of the pipe, we have another pressure force, but it's in the other direction. Also, because we have chosen the control volume like this, there is the atmospheric pressure being applied on the control volume. If you write the net force, this is net force, we're not setting it equal to MA or anything. We're just writing the total force acting on the control volume. So the total force is P1A1, 1, P2A2, 2, P2A2, minus the force acted by the atmospheric pressure, and the area is A1 minus A2 here, the area of the ring. If you rearrange this equation, just rearrange it, you get P1 minus P atmosphere times A1, P2 minus P atmosphere minus A2. And remember that we call this as gauge pressure because absolute pressure is equal to gauge pressure plus atmospheric pressure, the statics, fluid statics part, remember. So the net force acting on the system is the difference between the two pressure forces acting on the surfaces. Once a motion starts, I already said that there will develop a shear stress. Suppose that we are given two parallel plates like this. The parallel plates are very close to each other, and in between there is a flow. So if the upper plates is being moved, what happens? We have a bottom plate which is stationary, then there is a top plate, and in between there is a fluid. What happens if we move the upper plate?
It will cause the fluid to move as well.
Yeah, it will cause the fluid to move as well because fluid molecules stick to it. So their velocity must be equal to the moving velocity. At the bottom, because the bottom one is stationary, then the velocity must be 0. Then we can say that velocity starts from the plate velocity and goes to zero velocity. This is linear, but it doesn't have to be linear. But because we say they are very close, we can assume them to be linear. Otherwise, if the depth is very high, and if the plate is a ship, it's not possible to have a linear change of the velocity, right? So the velocity will be varying below the ship in just maybe 10 centimeters or 12 centimeters. Then there won't be an effect. But in the case where the distance between two plates are too small, then we can have a linear change of this velocity. And it was found that the shear force or the shear stress, which is F over A, F is the pulling force, is proportional to the velocity gradient. So velocity gradient is du over dy, the slope of this curve. The slope of this curve is actually du over dy, and the shear stress is proportional to it. If it's a line, if it's linear, what is du over dy? What is the derivative of a line? If you have a line as ax plus b, what is the derivative of it? A, right? A constant value. So in this case, if it's a linear variation of the velocity, its derivative with respect to y will be a constant. How about the proportionality constant between them? If I write 6 is proportional to 2, what is the proportionality constant here? 3, right? Because 6 is equal to 3 times 2. In this case, if shear stress is proportional to velocity gradient, then we have to have a proportionality constant, and this proportionality constant is called mu, which is viscosity. So viscosity is the proportionality constant between the shear stress and velocity gradient, which is the derivative of the velocity with respect to height. And for different fluids, you will have very different viscosities. Viscosity is the internal resistance to flow. So the higher the viscosity, the more it will flow. For instance, if you take out honey from the refrigerator, it's very difficult for the honey to flow, right? Because its viscosity is very high. But if you heat it up, it will become much easier for the honey to flow because its viscosity will be less and less. Similarly, when you start the engine of your car, the viscosity of the oil is very high because it's very cold and it's very thick. But after a while, when it's warmed, it will be thin. So it's important that the type of the oil is correct. Otherwise, when the engine gets hot, it may not be so easy for the oil to lubricate the engine. This is why the type of the oil is important. So if all the temperatures are about 60 Fahrenheit, crude oil, water at 100 Fahrenheit, air, as you can see, because the viscosity is just the slope of this line, so it's just tau over du dy. The highest viscosity belongs to the oil at 60 Fahrenheit. Water at 60 Fahrenheit has a less slope. Slope means the viscosity. Water at 100 Fahrenheit has less viscosity than water at 60. And air has the smallest viscosity. This was the dynamic viscosity. There is also kinematic viscosity, which is just dynamic viscosity divided by the rho. When you buy lubricating oil from the market, it may say SAE 30, and this 30 is actually a number related to the viscosity. So the lubricating oils are sold by their viscosity. An oil with a viscosity number of 30 is thicker than an oil with a viscosity number of 10. So SAE 10 is thinner than SAE 30, or SAE 90, which is a gear oil, is much thicker than SAE 30 or SAE 10, meaning that its viscosity is higher. So viscosity is actually the internal resistance of the fluid against flowing. Incompressible versus compressible, we have already said that if the change in volume is almost zero, we can call it incompressible. Otherwise, if it's changing its volume or density, because mass is rho times v, so if mass is constant, when volume is changing, density is also changing. Airflow can be considered to be incompressible if the velocity is less than 100 meters per second. So consider the air around the car. Is it a compressible flow or incompressible flow? If the flow velocity is below 100 meters per second for air, it can be considered incompressible. So consider a car moving on the street. So it's the same thing whether the car is moving or car is stationary, air is moving. They're the same thing. So if the flow velocity is below 100 meters per second, we call it incompressible. For the case of the car, is it compressible or incompressible?
Incompressible.
Why?
100 meters per second is a really high speed.
Yeah, it's 360 kilometers per hour. So normally, if it's not a racing car, it's an incompressible flow. How about the flow around an aircraft?
It most likely be compressible.
Yeah, most likely it's incompressible, compressible, meaning that at those speeds, the air in front of the aircraft will be compressed up to when? Up to the sound barrier, right? So yeah, they are related to sonic boom. If the compression continues up to a point where the flow rate becomes minimum, then we have the sonic boom, a sudden expansion. It happens at the speed of sound. So if the velocity of the aircraft becomes sonic, becomes equal to the speed of the sound, we have the sonic boom, meaning that there will be a sudden expansion of the air at this location. The second law of Newton states that if there is a motion, especially, not especially, an acceleration motion, the sum of the forces are non-zero. So it means that the applied forces, if they're non-zero, then it must be equal to m times a. In fluid flow, normally, remember the Newton's Reynolds transport theorem, we had the change of the momentum for the system is equal to change of the momentum within the control volume and net amount of momentum within the control volume and net amount of momentum coming in and going out. So you have a momentum flux as m dot times v. Normally momentum is mv, and time rate of it is either m dot v or m times a, because when you take the derivative of mv, you get ma. Also, if m is changing, m dot v artı ma, right? Chain rule. So if you have a incoming momentum flux, meaning that momentum per unit time is mv1 at the inlet, and if you have a momentum flux at the exit, then together with the forces acting on the control volume, it must satisfy the linear momentum equation or Newton's second law of motion. So as a mathematical expression, we can write it: time rate of change of momentum within the control volume, inside the control volume, the resultant force on the control volume, and net change of the momentum flux in and out of the system. This is exactly the same as the Reynolds transport theorem written for the momentum equation. So we can write this: if it's a steady state situation, this becomes 0. In this case, the net force will be equal to net change of momentum flux. So net change of momentum flux is m dot v2 minus m dot v1, and it's going to be equal to net forces acting on the system. What are the net forces acting on the system? They can be pressure forces, and they can be external forces, other external forces like gravity force, as if any. As an example, water flows over this nozzle. It comes horizontally and it leaves at an angle. So it's asking, what is the reaction force to be applied to the nozzle to keep it in place? Otherwise, if there is no force here, it would move, right? Because of the momentum change. So consider the jet ski. Jet ski is accelerating the water from the behind, and because of this momentum change, it applies a thrust on the jet ski and it moves. So similarly, this momentum change between the inlet and exit will create a force which will cause it to move. In order to prevent it from moving, there has to be a resistance, reactance force here, right? You need to hold it, otherwise it will move. Suppose you are a fireman holding a nozzle. If you leave the nozzle, it will move around like crazy, right? You need to keep it very tight because of the force it's applying due to the momentum change. So similarly, due to this momentum change, there has to be a reaction force to keep it stationary. So it's asking the magnitude of this reaction force to keep this nozzle stationary. So we suppose that the reaction force is applied like this. We don't know anything regarding the direction or magnitude, so we just assume that the reaction force has a x component fx and y component fy, and resultant is f. So we are going to calculate the value of the fi and fx and fy, which is necessary to keep the nozzle in place. According to the linear momentum equation, the sum of the forces is equal to net momentum flux, which is m dot times v2 minus v1. So because this is a vector, we have to write it in terms of sum of fx, which is m dot v2x minus v1x, and sum of fy, which is n dot v2y minus v1y. So we're just using the components of the forces as well as the momentum flux. Sum of x forces, as it's written here. Let's take a look at here. What is the momentum flux in x direction? It's this one, right? So it's n dot times v cosine theta. And this one is n dot times v sine theta. So for x directions, we will be using this, which is just n dot times v1. It's in the x direction. We will use that and also that. In y directions, there is nothing in y direction here. We will use this and that. So we will just write the forces in x direction and y direction. The x direction forces is n dot times v cosine theta minus v, which can be written as minus n dot v1 minus cosine theta. And y direction forces can be written as n times v sine theta, this and that one. So if we rearrange the formulas, the x direction reaction force must be this, and y direction reaction force must be that. They are given in parametric form. We don't know anything about the theta angle, and depending on the theta angle, we will see that everything will be completely different. For instance, if theta is 90 degrees, meaning that if the flow changes direction in 90 degrees, then FAX would be minus 52, FIY would be minus plus 59, 52, which means in this case, the reaction force will be like this, as we expect. If theta is 180, meaning that if the flow is reversing, then we get FAX to be minus 104 and FIY to be 0 because no momentum change in the y direction, which means we have to use a bigger resultant force to keep the nozzle in place.
Can I ask a question?
Yep.
So we are thinking of, let's say, the one where the flow changes as its direction as 180 degrees, right? But it doesn't do it instantaneously as it goes forward and backwards. It's curving.
Yep.
But if it curves inside as it's trying to turn around, wouldn't it also apply a force to the sides that will cause a rotational force?
Yeah, it's a friction force, but we do not take into account friction here. It's non-frictional force. In the case of friction, things may change, but we are not considering the shear force here. We have considered only the normal force, which is also not taken here because it's open to atmosphere. So they cancel. And there is no shear force because it's not given. We assume that the viscosity of the fluid is very small, very like 0. For instance, it's air. However, if it was like oil, a thick oil, then the viscosity would come into play and what you explain would happen.
How we can apply the friction at the equation actually?
Then if there was friction, it's not so easy, but because friction would affect on all the faces, on all the surfaces, then you should write the shear force, shear stress as a function of the path. Then in this case, the friction force would be tau times dA. You have to have a function of the shear force which varies with the path. Otherwise, you cannot do it. This one is a similar one. It's a horizontal pipe, horizontal elbow. Why horizontal? What would change if it was vertical?
Gravity would come.
Yeah, gravity would be also in the equation. So to make it simpler, it says that the pipe is horizontal. So in this case, the water comes this way and leaves that way. We're going to find out the reaction force to keep this elbow in place. Very similar to the previous one. What's the difference between this and that? This and the previous one? The previous one was open to atmosphere, so the pressures were canceling. However, here, the inlet pressure and exit pressures are different. So in this case, we have to take into account the effect of PA forces, the pressure forces. So the effect of PA forces, the pressure forces. So when you write the linear momentum equation, you will include the pressure forces as well. So some of, let's take a look at the axis first. This is the x-axis. So do you think there would be any x force here?
No.
No, because the flow is in y direction, so Fx is equal to 0 because there is no pressure force, there is no momentum component of the in the x direction, so some of the Fx forces is for sure 0. However, the y forces, and by the way, the y direction is this, so this is the y direction. This is the y direction. We have pressure forces in y direction as well as the momentum fluxes in y direction. So when we write, the first thing to do is to place the reaction force to keep the elbow in place. Then we have a positive pressure force. Why positive? Because it's in positive in x direction. The other is also positive. Why? Because if you take a look at the elbow from above, this is the pressure force being applied on this force. And even though the flow is in this direction, the pressure force is always taken as normal to the surface. So both of them is positive. So also the pressure force at the exit is positive. Then we have the momentum fluxes, because right-hand side should be equal to momentum fluxes. The sum of the forces should be equal to momentum fluxes. And V2 minus V1. V2 is in negative direction, so it's minus V. And V1 is already V. So if you rearrange this, you get the sum of the forces to be minus 2 m dot V plus P1 plus P2 times A. Most of the time, you may need to find out m dot first, and m dot, as you know, is rho times AV. So once you have this, and if you are given all the pressures, and if you are given all the areas, then you just need to find out the value of FAY. Because here you have chosen the AY to be positive as the solution, the AY turned out to be negative in the negative direction, which we expect, right? Because the reaction force should be in the other way. Like the fireman holding the nozzle, they should apply a force against the in the opposite direction of the flow. Flow go in the same direction actually, because the flow pushes the nozzle backwards. So they should apply a force in the positive direction. So this is similar to it. This is very similar to the previous problems, even though the drawing looks a little bit complicated. There is a faucet, and a nozzle is put in front of the nozzle. So when there is a flow, it's asking how much force this nozzle is acting to the faucet. So how much pushing force this nozzle is applying to the faucet. It's necessary to draw the control volume and free body diagram, of course. In the control volume, which is chosen to be this nozzle and the water in it. So here you have the pushing force due to the momentum change. You have the weight of the water inside the nozzle. You have the weight of the nozzle itself. Then you have pressure force here and pressure force there. Also, flow takes place downward. So when you write the linear momentum equation, you have to include all the forces with the correct directions. What I mean is, Fa is upward. This is for sure. This is the pushing force by the nozzle. The nozzle weight is downward. The water weight inside the nozzle is downward. P1A1, it applies on this face. This is the positive X direction, Z direction. So P is downward, whereas P times A is negative here, but here P times A positive. So P1A1 is negative, whereas P2A2 is positive at the exit of the nozzle. Then you have the momentum flux. Momentum flux is M times W2. W2 is the exit velocity in Z direction minus W1. And as we know, both W1 and W2 are in the negative direction, so they are both negative. So if you put everything in the formula, you get the necessary, you get the pushing power from the nozzle on the faucet to be as this. You just need to put the formulas, put the numbers in. Start with the M dot, which is rho AV. And AV is actually Q, which is the volumetric flow rate. So you are given the volumetric flow rate, you know the cross-sectional area, then you can calculate the velocities at the inlet and at the exit. Because it's a nozzle, you can see that it's accelerating because the cross-section is decreasing, it must accelerate. Then you can see that the force that the nozzle is applying on the system, faucet, is 77 Newton. It might be very confusing. This is the force that the nozzle is applying to the faucet. But for the faucet to keep it in place, there has to be an equal force, the resistance force, the reaction force, in the opposite direction. So this is not the reaction force as in the previous questions. This is the force that the control volume is applying to the surroundings. And to keep the nozzle in place, the faucet with the threads is applying the same force but in the opposite direction. Bernoulli's equation is a very useful, very practical equation, even though its assumptions may not be so realistic. It assumes that the flow is frictionless, there is no viscosity effect, so there are no losses. The fluid losses are because of the viscosity, friction. So in the application of Bernoulli's equation, it's assumed that there is no friction. And when you do this assumption, according to the Bernoulli's formula, the pressure of the fluid, rho v squared divided by 2, which is the kinetic energy of the fluid, plus gamma z, which is the potential of the energy of the fluid, is constant. So what it means, when the fluid particle comes from this point to that point, its total energy is constant. So this is just another way of saying the energy is conserved. According to the Bernoulli's equation, if it's a frictionless flow, then the total energy of the fluid is constant. This is the total pressure, but pressure is another version of energy. You can write this as pressure as well in another form. But in this case, the total pressure of the system is constant, or as I said, it's another way of saying total energy of the system, the flow is constant. So now that the total energy of the flow is constant, we can use it in several applications. First of all, we have to understand what stagnation point is. Stagnation point is where the flow comes to a stop. For instance, if you take a look at this baseball, right in the nose of the baseball, the flow comes to a stop, right? Or at the tip of the airplane, the flow comes to a stop. And other streamlines follow the path of the, or follow the shape of the ball, or follow the shape of the aircraft. So it means that now that the total pressure must be constant, what do you expect the pressure at the stagnation point? A fluid particle flows like this, right? With the total pressure of P plus rho V squared divided by 2 plus gamma Z, but let's say Z is constant, is flowing constant. So it's coming to a point where it stops, where it stagnates. So now that the total pressure must be constant, what do you expect the pressure to be here? Less than there or higher than there? It must be
higher.
It must be higher, right? Because this rho V squared divided by 2 is called dynamic pressure because of the flight, because of the flow. And this is the static pressure. And that one is the total pressure. What happens in the front of the airplane or the ball, what happens at the stagnation point is the total pressure increases. It's called the stagnation pressure. By using this principle, we can use the flow rates of the fluids, like pitostatic tubes. For instance, in this pipe, we have two pressure measurement tubes here. One tube shows this pressure. The second tube shows that pressure. Why do you think they are different? Because the fluid particle here has not only the local pressure, but also the dynamic pressure. But when it comes to a stop, we have P plus, P1 plus, we have P plus, P1 plus the dynamic pressure. So the difference between this and that actually corresponds to dynamic pressure. So if you're able to measure this pressure difference, then from this pressure difference you can calculate the velocity, and from the velocity you can calculate the flow rate. This is actually the classical method of the measurement of the speed of the aircrafts or ships. Ships have the most modern systems to measure their speeds, but they also have the pitometers, which relies on this principle. They measure the static pressure, they measure the total pressure, which is static plus dynamic. The difference between them is this, and once you know that, you can calculate the velocity. So this is a pitostatic tube. Here, at this location, you have a stagnation. Here you have the static pressure. So the difference between them will give you a relationship between the pressure difference and velocity, because rho v squared divided by 2 is equal to P1 minus P2. So by using this, you can calculate the V as 2 times rho delta P. So you just measure the delta P here, and by having the delta P in hand, you can calculate the velocity of the ship or velocity of the aircraft. An example of Bernoulli's equation: water is flowing from, or being emptied, draining from this container. So we take 2 points, point 1 here, point 2 here. We're going to write the Bernoulli's equation between point 1 and point 2. We know that P1 plus V1 squared divided by rho V squared divided by 2 plus rho gamma Z is constant. So if it's constant, it means that P1 plus V1 squared divided by 2 plus gamma Z1 is equal to P2 plus rho V squared divided by 2 plus gamma Z2. So this is what it means to have a constant value of these three pressures. In this container, if you write the equation between 1 and 2, what is the pressure at 1 and 2? The pressure here and pressure there. They are open to atmosphere, so they cancel each other, right? Then what else do you have? The difference of distance between this and that can be written as Z2 minus Z1 to be h, the difference. Then at the free surface, it's a large free surface. What do you expect the speed, velocity at the free surface if it's very large?
It would be very slow.
Yeah, very slow, or just take it to be 0, right? So this is 0 also. So at the end, you just get V equal to square root of 2 times G times H. So if you know the height of the water, then it means that you can calculate the velocity at the exit. Okay, we don't have enough time. Do we have any questions so far? We can continue from this point on next week. So I will stop here then. Have a nice evening and see you next week.